All right, so now we have 12.2. We're knocking them all out, right? Linear equations is done. And now we get into matrices, which is the fourth way to solve a system of equations. All right. So when we are given a system of equations, we can convert it to a matrix. And when you convert it to a matrix, you only put the coefficients and the constants. So the first column is for X, second's for Y, third is for Z, and the last is for your constants, your numbers without a variable. So you see how they transferred this linear equation into the matrix of X plus 2Y plus Z equal to 10. They only put the coefficients 1, 2, 1, and 10. Same thing with 2x minus 4y minus 3z equal to 3, 2, -4, -3, and 3. So this is how you will transfer any system into a matrix. The more equations, the more variables, the more rows and more columns you are going to have. Okay. So to solve a system of linear equations, we're going to use something called Gauss-Jordan elimination. We are going to do row operations, and we want to put our matrix into something called row echelon form. Row echelon form, which is this form here. So this is our goal today, to get our matrices into row echelon form. This means you'll have a bottom corner or a bottom triangle of zeros. And then you'll have a diagonal of ones. And then from here, A, B, C, D, E, F can be whatever numbers they want. What we want today, again, is this diagonals of 1 and these zeros down below. That's what we're going for. So this is the row echelon form. Okay. All right. And to get there, we're going to do a series of algorithms and steps, which is going to be super fun. It's very algorithmic. It makes you think it's a puzzle. It's a blast, guys. Okay. Okay. So let's try this out. Oh, yeah. Here's our operations on a matrix. So row operations, this is what we're allowed to do. We are allowed to interchange or swap any two rows. We can say take row 1 and put it where row 3 is, or put row 3 where row 2 is. You can move your rows around. 2, you can replace a row by a non-zero multiple of that row. That means it's elimination method. We can take any row and multiply it by any number other than 0. And then 3, replace a row by the sum of that row and a constant non-zero multiple of some other row. Once again, this is elimination method. So if we want to manipulate a row, we'll multiply another row by a non-zero multiple and add it to that row, and that will completely change a row. Now, what I'm saying to you probably doesn't make sense until we do it. So I'll show you how to do these row operations. So the first thing we want to do is convert our system into a matrix. So remember, your first column is for x's. So we have 2x, x, and 3x. So 2, 1, 3. And then the second column is for your y's, 2y, y, and 4y. 2, 1, 4. Third column is for z's. We don't have a z up here, so that's going to be 0, 1, and then -1. And then we put in our constants, 6, 1, 13. All right. So we have just transferred from system to matrix. All right. And now our goal is to change this into row echelon form. 1, A, B, 0, 1, C, 0, 0, D, and then E, F, A, B, C, D, E, F, G. Yes. So this is what we want it to look like. Okay. Okay. So here's what we're going to do. Our first row operation. We want to put a 1 in this top corner. That's our first goal. So what I'm going to say, in order to put a 1 in that top corner, is this row 1, I'm going to say 1/2 times row 1 will become my new row 1. So all we're going to do is multiply all of row 1 by 1/2. So with my new operation, I'll have 1, 1, 0, 3. And then everything else stays the same. 1, 1, 1, 1, 3, 4, -1, 13. And there's a row operation. We just put a 1 in that top corner. We're good to go. Now, the next thing we want to do is put a 0 right below the 1 in the second row. So we need to put a 0 down there. Now to do that, I'm going to say negative row 1 plus row 2 will become my new row 2. All right. So that means I take everything in row 1, multiply it by -1. So this is what I'm doing here. Let me see a little bit of side work here. So I'm taking -1, multiplying everything in row 1, and then adding it to row 2, which is 1, 1, 1, 1. Well, that becomes -1 plus 1, which will give me 0. And then -1 plus 1, which will give me 0. -1 times 0 plus 1, that's just 1. And then -1 times 3, -3 plus 1 gives me -2. This is now my new row 2. So when we rewrite the matrix, row 1 stays the same. 1, 1, 0, 3. And now I'm going to put the new row 2 in. 0, 0, 1, -2. And then row 3. 3, 4, -1, 13. Okay. All right. So we're moving. We now have the 1 and the 0. My next step is to get the 0 in the very bottom corner. That's what we want. So to get that 0 in the very bottom corner, I'm going to multiply row 1 again, this time by -3. So I'm going to say -3 times row 1 plus row 3 will become my new row 3. All right. So get my matrix ready. And this stays the same. 1, 1, 0, 3, 0, 0, 1, -2. And now we're manipulating row 3. So here's my side work again. We're taking -3 and multiplying row 1 by it. And then we're adding it to row 3, which is 3, 4, -1, 13. Distribute that -3. -3 times 1 plus 3, 0. -3 times 1 plus 4, 1. 0 plus -1, -1. And -9 plus 13, that is 4. This is my new row 3. And that's where I'm going to put that. 0, 1, -1, 4. All right. Now we have the 1, the 0, and the 0. But now my next step is I want that 1. Oh, wait, that shouldn't be a D, right? That should be a 1. My bad. That should be a 1. Okay, next thing is I want that 1 right in the middle. So what I'm going to do next is something quite easy. All we're going to do is take row 3 and swap it with row 2. Because if I do that, it'll put this 1 where it needs to be, right in the middle, right down that diagonal. So to do the swap, I'm going to say row 2 swap row 3. And when we do that, my new matrix is 1, 1, 0, 3, 0, 1, -1, 4, and 0, 0, 1, -2. And look at that. I now have my 1, 0, 0, my 1, and guess what? The next step we wanted is to put a 0 down here. Well, it looks like we have it already. And then the next step would to be put a 1 in that last corner, then that diagonal. And it looks like we have that already. So we have reached row echelon form. Now, all we want to do is convert it back into a system. And once we do that, you'll start to see the answers. So let's go ahead and convert row 1. And remember that your columns are X, Y, Z, and constants. So when I convert this back to a system, I get X plus Y equal to 3. And then row 2 becomes Y minus Z equal to 4. And then row 3 gives me an exact answer that Z is equal to -2. There's our first answer. And now all I have to do is plug it into the second equation to solve for Y. And then I take Y and Z and plug them into the first equation to solve for X. So there we go. I'll just say find Z, and you'll have Y minus -2 equal to 4. Y plus 2 equals 4. Therefore, Y equals 2. And then find X. We get, oh yeah, it's right there since I have Y. I have X plus Y which is 2 equal to 3. Move that 2 over, and x equals 1. There we go. And that's how you solve a system of equations using a matrix. Okay. And our solution, I don't know if my math lab's going to make you write them out as x equals 1, y equals 2, and z equals -2, or it may make you write it as a point. 1, 2, -2. All right. How are we feeling after that?
I'm assuming for this example of matrices, if we were to add a fourth row, we would just, instead of 2 zeros, it'd be the 3 zeros and then the 1, and then whatever variable we were looking for.
Yeah, so we keep expanding that diagonal.
Okay.
And those zeros, yeah. All right, what else? Oh man, we lost people on that one. Matrices, they make your life better. And matrices are used in most advanced mathematics because they just get the job done a lot faster.
They're definitely
Also,
a lot more fun.
Yes.
You get a lot of really like cool results for stuff that let you figure out some really important things about systems of equations, and just make the work so much easier. Like stuff that literally isn't solvable with other sorts of like calculus or something like that. You can design a matrix the right way using linear algebra and get results very quickly.
Yeah.
I don't know if you know what cool means.
It's very cool, man.
It's not cool like kissing your sister cool, but it's cool to me.
Yeah, love it. All right. Yeah, so matrices are definitely using the advanced mathematics when you get to higher courses. But they're crazy, man. You can do a lot of crazy stuff. There's stuff you can find in there, like things called eigenvalues. Look those up. They're pretty insane. But also, if you want to get crazy and just practice matrices more, you can go for something called reduced row echelon form, which definitely takes a little more work. But reduced echelon form would be just the ones and diagonals and constants. So you'd have 1, 0, 0, 0, 1, 0, 0, 0, 1, and then A, B, C. And you'd have to do a couple more row operations to get there. And this, in reduced row echelon form, would put everything exactly as the answer. X equals A, Y equals B, and Z equals C. So definitely you can put in the time to do that. Today, it's just regular row echelon because we're just learning how to do these methods. Okay. 20 minutes left. Oh, let's do it. Matrices turbo time. All right. So there's our system again. Convert to matrix. We got 1, 2, 3, -1, 3, -2, 1, -1, -9, and then 8, -2, 9. Make sure you put everything in properly. Don't miss a sign. What are you doing back there? 1, -1, 1, 8, 2, 3, -1, -2, 3, -2, -9. Okay. And then, of course, I'm going to put the form there so it just reminds us what we're going for. 1, 0, 0, A, 1, 0, B, 0, 1, and then, actually not 0, B, C, then D, E, F. There we go. Last time I had a G in there. All right. let's do it. So our first goal is to get a 1 in that top corner. Well, mission accomplished. Then the next goal is to get the 0 below the 1. Get both zeros below the 1. So to make matrix C operations faster, you can do multiple operations at the same time, which is pretty cool. So what we're going to do here, we're going to change row 2 first. We're going to make that 2 into a 0. So I'm going to multiply row 1. I'm going to say -2 by row 1 plus row 2 will become my new row 2. And then at the same time, I'm going to say -3 times row 1 plus row 3 will be my new row 3. All right. And with that being said, here's my matrix. Row 1 stays exactly the same. But now, side work. Here's the operation. It's -2 times everything in row 1 plus row 2. 2, 3, -1, -2. -2 times 1 plus 2, 0. -2 times -1, +2 plus 3, 5. -2 times 1 plus 1, -3. And -16 minus 2, -18. So there's row 2. 0, 5, -3, -18. Okay. And then let's do it for row 3. So same thing, -3 times row 1 plus row 3, which is 3, -2, -9 and 9. And -3 plus 3, 0. +3 minus 2, 1. -3 minus 9, -12. And -24 plus 9. -24 plus 9, that's -15, right? 0, 1, -12, -15. Dun, 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 dun. Look at that. 2 row operations at the same time. And we have the 1, the 0, and the 0. And now I need to get that 1 right in the middle. So I can do a row swap. Why not? We'll just say row 2, swap row 3. And I have 1, -1, 1, 8, 0, 1, -12, -15, 0, 5, -3, -18. Okay, and we have it. 1, 0, 0, 1. And now we need to make that 5 into a 0. So we're going to do another row operation. We're going to manipulate row 2 and add it to row 3. So I'll say -5 times row 2 plus row 3 will become my new row 3. 1, -1, 1, 8. 0, 1, -12, -15. Come on. My pen's like, stop it. No more. All right. And then let's do this. Side work. It's -5 times row 2, 0, 1, -12, -15, plus row 3, 0, 5, -3, -18. And that's 0. That's 0. That is 60 minus 3, 57. That's 75 minus 18. That is also 57. So there you go. 0, 0, 57, 57. And we have 1, 0, 0, 1, 0. And all we have left to do is make this into a 1 in the bottom right corner of that diagonal, which means we're going to do one easy row operation. We're going to say 1 over 57 times row 3 will be the new row 3. And here we go. 1, -1, 1, 18, 0, 1, -12, -15, 0, 0, and you're multiplying all of these by 1 over 57. So you get 1, 1. And we got it. We have our row echelon. 1, 0, 0, 1, 0, 1. We have it. Now convert back to a system. Row 1 is x minus y plus z equal to 18. Row 2 is y minus 12z equal to -15. And row 3 is z equals 1. There we go. And then to find y minus 12z times 1, add that 12 over, and y equals -3. And then to find x minus y plus z equal to 18, x plus 3 plus 1, that's fine, equal to 18, that is 4. Move the 4 over. Did I change that to 18? That should be 8, right?
No, it's 18. Oh, it is 8. Never mind. Yeah.
It's 8.
You changed
Yeah.
it to 18.
Yeah. I just changed it to 18. I was like, that doesn't look right. And that's x plus 4 equal to 8. Move that 4 over, and x equals 4. Much better. There's your solutions, or write it as a point in the XYZ coordinate system. 4, -3, and 1. Boom. So much fun, guys. Isn't that better than taking an equation with another and then putting it in terms of x and y, or x and z, or y and z, and then taking another two and putting that in terms of x, y, or z, and then putting those two? It's all fun. It's good. So systems are crazy.
There's a lot of side work involved though.
Yeah, but I mean, you get faster at it. Like you're like, because you can be like, hey, -3 times all of that plus all of that gives me the row 2 already, just by looking at it. But of course, write everything down if you need to. There is a bunch of side work. Okay. And you can always check your work by using a matrix calculator, which Carl likes, right?
I mean, I do it all by hand, but because I'm insane. Also, I don't really have a choice but to do it by hand
Yeah,
if I'm actually going to use the matrices.
I mean, you guys still definitely have to show work, but look at this. Where am I? Go back to regular Desmos. Leave. Why'd you do that? No. There we go. And look, if you go to Math Tools, watch this. Oh my goodness, a matrix calculator. But again, you still have to show all work. So I'll say new matrix, and I have 3 rows, which I can edit down there, by 4 columns. And I'll type in my values. 1. No, stop popping up. It's going to pop up every time, I bet. Yep, that's annoying. 1, 8. 2, 3. -1. Maybe I'll just use that. -1. And then you have to do that. I try to look how to turn the keyboard off, but I can't. It just pops up when it wants to. 3. -2. -9. And 9. And then I'll say, oh yeah, it doesn't do row echelon. I guess it only does reduced. So we'll just say reduced row echelon form of matrix A, and we should get the same answers unless I mess this up. We should get 4, -3, and 1. And look at that. 4, -3, and 1. It's beautiful. All right, cool. All right, everybody go with that? There's like 5 minutes left. Definitely turbo math on the last one. Or just use the calculator. All right, let's see my matrix. 6, -12, 5, -1, 2, 1, -1, 2, -1, 4, -8, and 3.
That's a dependent system.
Oh yeah, that'll be fun. See if we can explain that in 5 minutes. Is this going to be nice to us? I need to get that to be 1. And so I'm going to say, let's see, negative row 3 plus row 1 will be my new row 1. And then if I say that, that means -5 plus 6 is 1. -1 plus -1 gives me -2. +1 plus -1 gives me 0. And -3 plus 4 gives me 1. All right. And then in, yes, they do. And then in the same move, I'm going to say, let's get a 0 in that middle column. Oh, I should have waited. No, I can divide by 2. Never mind. Yeah, actually, yeah. Let's do that. I'm going to say -1/2 times row 2 will become my new row 2. So I just divide everything by -1/2, and I'll get 6, -1, -1, 4. And then I'll have to stop there. So 5, 1, -1, 3. All right. And then next, we have the 1 there. Those need to become zeros. So I'm going to say -6 times row 1 plus row 2 will become row 2. -5 times row 1 plus row 3 will become my new row 3. So this stays the same. 1, -2, 0, 1. And -6 plus 6 is 0. +12 plus 1 is 11. 0 plus -1 is -1. And -6 plus 4 is -2. Beautiful. Next, -5 plus 5 is 0. 10 plus 1 is 11. 0 plus -1 is -1. And negative 5 plus 3 is negative 2. Woo! There we go. We're moving. And then next, I'm going to make the bottom row into 0. So what we're going to say next is negative row 2 plus row 3 is equal to my new row 2. No, sorry, row 3. Row 3. And this means I get the top one the same. 1, negative 2, 0, 1, 0, 11, negative 1, negative 2, and then 0 minus 0 plus 0 is 0. Negative 11 plus 11 is 0. Positive 1 plus negative 1 is 0. And positive 2 plus negative 2 gives me 0. All right. Now we see that we have zeroed out a whole row. So let's go ahead and convert to a system. This will be x minus 2y equal to 1. This will be 11y minus z equals negative 2. And we see that we don't have any coefficients for z. So what this translates to is 0 equals 0, which is a true statement, which means that we can say z is free. It's free to be any number it wants because it will make all of these equations true. So now what we do with that is we're going to solve each equation for x and y. And yeah, so that's what I'm going to do first. So I'll take this equation, 11y minus z equal to negative 2. I'm going to solve it for y. 11y equals z minus 2, and then divide by 11. So y equals z over 11 minus 2. So here is the answer for y. What did I do? Oh, over 11. Yeah? All right. And then x minus 2y equals 1. Solve for x. X equals 2y plus 1. But y is equal to this. So we're going to have to plug that in. X equals 2 times z over 11 minus 2 over 11 plus 1. And we'll get x equals 2z over 11 minus 4 over 11 plus 1. Now just put negative 4 over 11 plus 1, and I'll get 2 over 11z, and that's 11 over 11, gives me plus 7 over 11 as our answer for x. So since we don't get an answer for z, since we get a true statement that says 0 equals 0, this means that z can be any number it wants to make all these equations true. So this is a dependent system. And there we go. All right.
And pretty much geometrically, what that would look like, because these are all 3D shapes, is you would have two planes, which is the 3D version of a line, that intersect infinitely along the z-axis somewhere. So you'd have to find wherever these two z lines make a line in 3D space, and then the x and the y would intersect on those lines, on that solution of those two lines infinitely.
Whoop, whoop. What?
And then you can do that in Calculus 3 if you want.
What programs do 3D?
GeoGebra.
GeoGebra?
Yeah.
Think it'll do it? Or we'll
yeah,
break
here.
it?
No, I got it here. I'll load it
You
up.
got
It's
it?
kind of hard to tell. Yeah, let me load it
Alright.
up real quick and then I'll show it. Let's do 3D graphing. what do you call it? The one for Desmos is just like not very good. So we got 6x minus y minus z equals 4. And then we got negative 12x plus 2y plus 2z equals negative 8. And then our last one is 5x plus y minus z equals 3. Okay. Change these colors. Yep. And then this one, color, make it green. Okay, cool. So this is sort of the best you can do. Share my screen real quick.
Yeah, do it. Let's see.
This
Let's
is
see
sort
how
of
cool.
the best you can do with the 3D system, right? But if we, whoa, okay, so the first one is that blue one, right? And then the second one's the red one, and then the bottom one, the third one was the green one. So even if you zoom out, you can't really see very well, but you get planes, right? They just continue infinitely in two directions, and they're flat and infinitesimally thin, right? As opposed to some 3D shape, but they're going to intersect. Let's see, they intersect everywhere on the, looks like the green one, right? As you just keep scrolling out here, you see that the green one is always going through this red and the blue one at pretty much the same point, no matter what. No matter, so we're out here at like negative 1600, negative 2000, and it's still intersecting on that red line or that green line the whole way through. And it's just going to keep doing that infinitely forever, no matter where you go. And that's what it means to have a free variable. If you had a one solution to this at one point, there would be one very obvious point where the three of them intersect and they wouldn't intersect anywhere else. So yeah, that's
Cool.
pretty much that.
There you go. Visual representation of what we're doing. Okay. So that means we are done. It's 8:45.